The second type of switching power supply that we're going to consider is our boost converter. And so our boost converter is going to behave opposite of how our buck converter did, in that our boost converter is going to raise the input voltage compared to our Vl. So raises input voltage. Now, because of conservation of energy, if we're going to be raising our input voltage, while we're doing this, we're going to be lowering the average current draw. So it also lowers the average current drawn from the power source. So what we can see in this basic circuit diagram here is we have the same components that we did for our buck converter. They're just arranged a little bit differently. So we still have our inductor, our diode, and our capacitor, and our switch. And so let's go ahead and label some things. As you can see, I've got some plots ready below. So let's go ahead and label a few items here. So we're going to have our output current over here. We can label a diode current, I sub D, a switch current, I sub S in our switch, and an inductor current, I sub L, and an inductor voltage, V sub L. And so if we think about the basic operation of this circuit, we can see that while our switch is closed, our inductor is going to be charged up by V raw. So during this time when the switch is closed, our diode D is preventing any energy that is stored in the capacitor from coming back in this direction. So when our switch opens, of course, remember our inductor current cannot change instantly. So it begins discharging through some of that stored energy through our diode and charging up our capacitor and or delivering current to our load. Once the switch closes, again, our inductor sort of becomes isolated from everything else, and our capacitor is then delivering energy to our load. Again, while this diode is preventing energy from coming from the capacitor towards the left side of the circuit with the inductor and the switch. Okay, so just like with last time, we're going to make a couple assumptions about these sort of elements in our circuit. So we're neglecting pretty much any losses in our circuit. So let's just note that explicitly. So we're neglecting losses in our inductor, our coil. We're neglecting losses in our switch. We're assuming that it happens instantaneously. And we're also neglecting any diode losses. So we're assuming that our diode doesn't have any voltage drop, doesn't have any reverse leakage current. Another thing that we're going to assume when we come down here to these plots is we're going to assume that the circuit is in steady state. And so what that means is, of course, we're going to have an initial sort of charge up when we the very first time we sort of open and close this switch, but we're assuming it's been opening and closing for a long time, and we're sort of coming in to look at this at the middle of the operation. So we're assuming it's in steady state. Okay, so let's look at some of these waveforms. So just like with last time with our switch, we're going to have sort of just two basic cases, on and off. And so in this case, of course, our on is going to be, and I'll put this over here in parentheses, our on is closed and our off is open. And so notice I've got sort of the main variable for our y-axis on all of our plots highlighted, just so we don't get it confused with all of the value notation. So for instance, we're not getting switch confused with our on and off there. Okay, so let's say we have some type of switching waveform that looks something like this. So maybe it's off for a little bit, and then we close it, so it comes up here to being on, and then it's on for a while, and then we close it again, then it's off, and then over here we switch it open again. So we have something that looks like this. So just like with last time, we can define our T on and our overall period. So this would be our T on, and this would be our T, capital T, our period of our switching waveform. And so we didn't deal with this in our last case, but we'll see we have a definition based on this T off time as well. And so this definition, we'll get to it in a little bit, but it's not explicitly shown in your textbook. Okay, so that's what our switch is doing. So let's talk about our inductor voltage VL. So similar to last time, we're basically just going to do a KVL loop. So if our switch is open, as we see it is for the very first part of that switch plot, what we're doing then is a KVL around this whole outside loop. And again, remember, we're assuming our diode is lossless, so we don't have any voltage drop there. So from KVL, our VL is going to be V raw minus V naught. So we come down here, and we can say we're going to have some value down here, V raw minus V naught. And so remember, we're stepping up, so our V naught is going to be higher, so that's why I've drawn this negative. And so we're going to be negative until our switch closes. And when our switch closes, let's come up here. So if our switch is closed, then we're going to be doing our KVL here instead of around that full loop. And so from that, we can just see our VL is going to be equal to V raw. So coming back down here, for our inductor voltage, we can add our V raw here. And so I've not necessarily drawn these to scale, and of course it's going to change depending on our particular circuit as far as what these values are. So that's going to switch up to V raw. And then as long as that switch is closed, it's going to stay at V raw, and then it's just going to drop back down to the previous value when it opens, and it's just going to alternate with that switching waveform like this. So pretty similar to what we've seen with our buck converter. Okay, so now we want to look at three currents. We want to look at our switch current, IS, our diode current, ID, and our inductor current, IL. Okay, so we know that our inductor current, this bottom plot, is going to have to be continuous, and we don't have the same restriction for our switch and our diode, however. So for all of these plots, we're going to have sort of two currents of interest, the same as we did with our buck converter. We're going to have some upper limit I2 and some lower limit I1. And so these are going to vary again based on the design. So I'm drawing them so that they should be equal. So I'm trying to get them as equal as possible between the three plots here. But we're going to have some upper and lower current. That's going to be limiting all of these current values. Okay, so let's think about, I think maybe it makes the most sense to talk about our inductor current first, because that's the one that's going to be continuous. So again, we're saying that this circuit was in steady state, so we've come in after it's been switching for a long time. So let's say it's in this open switch state, and our inductor has been charged up previously when the switch was closed, but now the switch is opening, so it's beginning to discharge some. So our switch is open, and our inductor is discharging. And so what's happening is we're discharging until we get to this point where our switch is about to open, and at that point we've reached our minimum current of I1. So at this point, our switch closes, so we're talking about this transition here, our switch is going from open to closed, and what that means for our inductor is now it's charging up, now our current is increasing. But again, that current can't change instantly. So what's happening, and let me kind of draw a guide here, so I want to go to this point. So now our current is increasing to some maximum value of I2. Okay, so let me get rid of that. So that's just to help me line up my plots. At which point our circuit is opening again. So now we begin discharging. And so we're going to discharge until we get to here when our switch opens again. And so again, our inductor current has to be continuous, so we get something that looks like that. So it's reached I1 again. And then our switch is going to be opening, our switch is going to be closing again. So we're talking about this transition here. So with our switch closing, our inductor begins charging up again towards I2. So we get something that looks like that for our inductor current. So it's sort of just alternating between I1 and I2. So now based on that, we can sort of figure out what our diode and switch currents look like, sort of one at a time. So let's look at our switch current first. So if our switch is open, of course, we're not going to have any current in that. So everywhere that our switch is open, so if we look at our switch plot, that's going to be here and here, we're just going to have zero switch current. So we're going to have zero current here, and roughly zero current here. So again, I've tried to align these all so they're the same the time is sort of aligned here. Okay, so now whenever our switch is closed though, it's in series with the inductor. So if we have our switch closed, we just have one series path here for our inductor, so that means that the switch current is going to be the same as our inductor current. So we look for those two regions and we say, well, from this point, we have an inductor current of I1, and at this point we have an inductor current of I2. So that's what our inductor current looks like, and in our switch we can have instantaneous changes. So we get something that looks like this. And so of course that's just repeated over here. So it jumps up to I1 when that first opens, and then it's increasing towards I2. Okay, so now how about for our diode? Well, our diode, let's first consider the case when our switch is closed. When our switch is closed, all of this current from the inductor is flowing in this direction. And remember, our diode is essentially just blocking current from coming this way. So it's saying you can't come this way. And so in that sense, the only current we have would be our reverse saturation current. But remember, we're neglecting our diode losses, so we're just saying that's zero. So what that means then is that for the cases when our switch is closed, which is going to be right here, we're saying we have zero diode current. So coming down here, we have zero diode current roughly right here and right here. Okay. When our switch is open, so if we have our switch open, we can see that any current going through the inductor is going to go through our diode as well. So they're in series in that case. So what we're going to have is our inductor current is equal to our diode current. So we sort of look at this and we say, well, in this case, it was decaying down to some value, and at this point it was I1, and then it drops instantly down to zero. We look at this point here, and we see it's at I2, so we come up here, we say our diode current has to be equal to that, so it instantaneously jumps up to I2. At this point here, our diode current is at, or our inductor current is at I1, so that our diode current is also at I1. So we have something like that, and then an instantaneous drop down to zero. Okay, so this is sort of what our basic current waveforms would look like. One thing to note is our diode current is not necessarily equal to our load current, so it's kind of hard to visualize if we've not put any load in there, but for our simplest case, we can think about having a load resistor. And so of course, if we have a load resistor and this capacitor has been charged up, our capacitor essentially acts like a battery, and it's going to be giving energy to that resistor. So that's like our RC natural response. So just something to keep in mind in terms of our output current is not necessarily equal to ID. One other thing I want to note too while we're looking at this plot is we have the same definitions for discontinuous and continuous mode. So same definitions for our continuous and discontinuous modes. And so that's same as what we saw for our buck converter. And so we're talking about our inductor current here. And so remember, for our continuous mode, that means our I1 is basically greater than zero. We're never dropping down to zero. Discontinuous means our current in the inductor is reaching zero for some amount of time. Ideally, we want to be in continuous mode. If we're in discontinuous mode, that just makes our analysis a lot more difficult. Okay, so now let's talk about some equations related to this. So we're not going to go through and do the derivation of this, but basically we can show that our output voltage for our boost converter is equal to capital T over T on times V raw, which we can also write as V raw divided by 1 minus D boost. Okay, and so D boost is something I'm writing there for the first time, so you should be asking yourself, well, what is D boost? So we define D boost to be equal to T off over T. And so what this is this represents the duty cycle of the circuit. So this is the duty cycle of the circuit and not the switch. So basically, if we come back up here to our circuit briefly, what we're saying is we want to sort of have a duty cycle that indicates when the inductor is connected to the output side of our circuit. And so we can see that happens when our switch is open. And so our switch is, of course, open when we're talking about this T off part. And so that's why we define this duty cycle a little differently than how we did for our buck converter, because with our buck converter, the switch was in series between our input and output. So we have this D boost defined as T off over T. And so one thing to note as well is typically we want to keep this D boost to be less than 0.9 for the same reason that we talked about. So let me just say typically, because if our D boost is getting greater than that, we're talking about stepping up more than 10-to-1 ratio. And so what happens then is our on switching and off switching times become non-negligible, and we have some issues in our approximation. So like we talked about with buck converters, you can put multiple circuits in cascade to get around that issue. So another important equation is related to our ripple voltage. So if we make the assumption of a constant output current, so our output current I0, what we get is we can find our V ripple, or we could also define that as V boost, is equal to whatever that constant output current is times our D boost, the duty cycle of the circuit, divided by the frequency of the switching times the capacitor. And so typically for a good design, we want this V ripple to be less than 10% of V out. So that's for a good design. But like we've talked about before, it really depends on our application, right? So if we're powering, if we have a high gain amplifier, of course, we probably want to get that much less than 10%. Whereas if we're using this for some type of lighting or heating element, maybe we can go a little more than 10% and it's not going to really be too much of an issue. So something to keep in mind there. One other note that applies to both our buck and boost converters. So let's just say for both buck and boost converters is that we can apply feedback and we can sort of measure our V output, and from there we can adjust our duty cycle in order to adjust the output voltage compared to some reference voltage, which is what we want. So they can use feedback to compare our output to a reference, and then once it does that, it can adjust our duty cycle as needed. So remember, if we're adjusting the duty cycle, so for instance here we're adjusting this D boost, and if we adjust this D boost, we're of course adjusting the relationship between our V out and V raw. And so similar thing with our buck converter.